guys, welcome to the video on concentric objects, where you try to find the electric field inside, between, and outside of a system of charged objects, usually spheres or cylinders. All right, now to orient you in your notes packet, you should be on example 19. This is the diagram that you would show with it, so if you kind of want to get caught up and draw the diagram if you haven't already, then go ahead and pause me and do that. More or less, the idea here is you have some kind of a sphere hung in the middle here, another hollow sphere around it. The way it describes constructing this is you take a sphere, hang it from a string, and then take two metal hemispheres and go clump around it on either side, and now, boom, you have concentric spheres. All right, that's more or less the premise of how they're put together. The middle one here in this particular question is charged and has a charge of +2 microcoulombs. All right, the first thing that I want to get out of the way in general with these questions about concentric objects is the premise of what happens to the two surfaces on this outer object, assuming, of course, that it is a conductor. All right, now, if it's not a conductor, I'm not even going to talk about those in this video because those problems are just an excuse for atrocious algebra, just horrendous, right? So if the outer object's an insulator, forget about it. I won't even look at that in this video. But if the outer object is a conductor, here's what's going to happen. Because this one is, I don't know, let's say plus Q, we'll just call it Q for the moment. The electrons that are in this conductor are going to notice that positive charge in there in the very middle, and they are going to begin, let's say, crowding around this inside surface, resulting in the inner surface of this acquiring a net charge of -Q, obviously spread out over that whole area right there. All right, now I am not saying that charge is being created. I am saying that this inside surface is always going to end up becoming equal and opposite to whatever charge exists on the central object that is placed in the middle of this outer object. All right, so if this is a plus Q, this is going to take on -Q, whatever that is. All right, and obviously if this were a -Q, then the reverse would happen. Electrons would look at that and be like, ugh, and move away to the outside surface, leaving you with a positive charge on the inside. Okay, so whatever happens, this object and the charge on the inside surface are always going to end up being equal and opposite. All right, now, the outer surface of the outside object will acquire its own charge, and the two charges on these two surfaces are going to need to always add up to whatever they say the total charge of the outer object is. All right, let me write down some labels here. We have really three different things that we're looking at. You have the inside object, right? The thing that's in the middle. All right. Then you have the outside object. This outside object has an inside surface. So if you imagine you were like standing in here, right? Here's a little person in here, right? There he is standing on the inside surface. All right. And then this outside object also has an outside surface, which you could imagine someone standing on the outside with a really long arm touching it. There, okay? And now he starts pushing on it and rolling it, and this guy has to run and keep it. Sorry, okay, anyway. The outside object has an inside surface and an outside surface. Those two surfaces can have and will have probably different charges. But whatever those two charges are, they have to add up to the total charge of the outside object. All right, so let's suppose that the charge of the outside object is 0. In this circumstance, where I said the charge on the inside surface becomes -Q to match this one, that would mean that the outside surface would have to take on a charge of plus Q in order to add up to 0. All right, on the other hand, if they say that the charge on the outside object is, I don't know, how about negative Q, and the charge on the inside surface is negative Q, the charge on the outside surface would in fact be 0. It wouldn't be charged at all. I could make up any combination of things here. Like you could say maybe the outside object has a charge of, how about 7Q, not 70, 7Q. If the inside surface is minus Q, because it has to be equal and opposite to that one, and the two surfaces have to add up to 7, positive 7, this would be plus 8. All right, if that didn't make perfect sense, you should pause the video, back it up, and play it back a few times until it does make sense, because that's really a pretty central idea, right? That you've got two objects. You can talk about the charges of the objects as a whole, but then this object has two surfaces, and those individual surfaces can have their own charges, but they must add up to the charge of the outside object. All right, so replay that to yourself, make sure that it makes sense before we move on. All right, now, example 19 asks you to do several things. Mainly, it's find the electric field at a bunch of different distances. The question here is giving you this information, right? It's telling you the radii of various objects, and then it says find the electric field at several distances. All right, first thing is always to figure out where that is. You need to know if you're inside of an object or outside of an object in order to do Gauss's law. Because Gauss's law is all about what is the enclosed charge, right? If you can't figure out the enclosed charge, then you're in big trouble. All right, so it says the inside object has a radius of 3 centimeters. There it is, 3 centimeters. We're supposed to find the electric field at a distance of 2 centimeters from the center. All right. And furthermore, the inner sphere is a conductor. All right, now, at this point in the unit, you should be savvy on the fact that that means that the electric field is automatically 0. The electric field inside of a conductor is actually always 0 because the charge on a conductor always lives on the outside surface, right? So if this is where all the charge is, then there is no charge in here. Therefore, Q enclosed is 0, and the electric field is 0. All right, B, find the electric field at 5 centimeters. All right, well, we'll still use Gauss's law, but 5 centimeters is like somewhere out here. All right, there's 5 centimeters. All right. In this case, since it's spheres, Q enclosed would be whatever the charge of this sphere is. In the prompt, I find it as plus 2 microcoulombs. I do not, in fact, have to do anything with density functions in this circumstance because we are answering a question related to being outside of a sphere. If you recall, one of the quirks with spheres is that if you're outside of it, you don't have to worry about the density functions. You just say the enclosed charge is all of it, the whole charge, whatever that is, and they'll usually, for a sphere, tell you what that charge is. All right, so 2 microcoulombs. A. All right, remember the A here is always the surface area of the Gaussian surface. That's the thing that I've drawn in red, okay? The Gaussian surface there is a sphere, 4 pi little r squared, where the little r is going to be, in this case, 5, because that's the radius of my Gaussian surface. All right, now I'll save you the trouble of typing in numbers and whatnot when I divide and all that, and plug in r equals 0.05. We're apparently going to get 7.2 times 10 to the 6th newtons per coulomb. Right, now notice, at no point in A or B did I even care about this outside object. That's because if it's not enclosed, Gauss doesn't care. If it's not enclosed by the object, Gauss would say nobody cares about that. Was it enclosed? No, I don't care. Okay, all right. Well, then I don't either. If Gauss doesn't care, then no one cares, all right? It doesn't matter what this object is until our Gaussian surface is large enough to start including some portion of it. All right, which sort of brings us to our next part. We need to answer C, but then we'll get to D, right? If you were paying attention to my discussion moments ago, you should be fine with, okay, if this inner object is +2 microcoulombs, then the inside surface of the outer object is -2 microcoulombs, equal and opposite. The outside surface of the outer object will end up being +2 microcoulombs because they said its charge is 0. All right, now I've got all my charges labeled. All right, so let's move on to D now. D wants to know the electric field at 10.5 centimeters. Again, if we've looked carefully at the prompt, the inside surface of the outer sphere is 10 centimeters away. The outside surface of it is 11 centimeters away. That means 10.5 is in the middle of this conductive material. And what is the electric field inside of a conductor? If you answered 0, you're correct. That's right. It's 0. We're in the conductive material, so the electric field must be 0. All right, now, the reason that it's usually 0, we said, is if the enclosed charge is 0, then that means the electric field is 0. Often with conductors, that means that literally you aren't enclosing any charges. In this case, the reason's slightly different. We are enclosing a 2 microcoulomb charge. But we're also including a -2 microcoulomb charge from this inside surface of the outer object. That's 0! The net charge enclosed by this Gaussian surface drawn at 10.5 centimeters is 0. So therefore, there's no electric field at this distance. All right, part E. What's the electric field at 15 centimeters? All right, 15. That's out here. All right, if I now do my Gauss's law again with that distance, actually what, you can pause the video, go ahead and see if you can work that out on your own. Great, pause me, work it out. All right, and here we are with the work. Mr. Erico, you just took part B and you crossed out B and put E. Well, yeah, like the work's about the same. I mean, it's still spheres. We're just like at a bigger, different distance. Oh, and potentially we might be enclosing a different amount of charge, but it depends on how the question is set up, all right? In this case, the amount of charge we're enclosing does end up being the same, but only because if I do 2 minus 2 plus 2, that's still 2 microcoulombs. You can see, here was this charge, and here was this charge, and here was this charge. These two always are going to cancel out. So the Q enclosed really just ends up being whatever's here on the outside surface, which, remember, doesn't necessarily have to match this. If they had said, right at the start, Q net is like, I don't know, plus 4 microcoulombs, then this would have been 6. So that the -2 and the 6 could add up to the 4 that I hypothesized there. All right, and then if that were the case, then we would have been plugging in 6 microcoulombs here. All right, we weren't doing that. They didn't do anything funky like that, so there we are. Plug that in, plug in a new distance, and you should have gotten 8 times 10 to the 5th newtons per coulomb if you work that all out correctly. All right, now the last part of this question wants us to construct a graph of the electric field. For the electric field, if you recall, the sort of classic appearance of this for a conductor was like, all right, flat line, jumps up, and then kind of does that, right? Meaning inside of a conductor, there's no electric field, has a value of 0. But as soon as you reach the surface, it suddenly jumps up to whatever the maximum value is, and then drops off as you move away from it, because after all, as R gets bigger, E is going to get smaller. All right, fine. Now, this one's a little bit more interesting, and we have several other R's that we've got to label here, but still this basic idea is going to be correct. Inside of a conductor, there's no electric field, and that the electric field should decrease as we move away from the charged objects. So the distances I'm going to label here are going to be 3 by 3. Oh, because 3 is the radius of the inside object. 10 and 11, because those were the inside and outside radii of the outer object. All right, so here goes. My graph of electric field is 0 at first. There's no electric field inside of that central conductor. Boom, the electric field jumps up to some high value, and it's going to decrease as we move away. And then it's going to be suddenly 0 when we reach this outside object. So boom, fall all the way down to 0, right? And then it's 0 this whole time, and then it will pick up again once we leave the object. All right, now this last part of the graph is potentially where it's tricky. How high up you jump and whether you honestly go up or even potentially below the axis depends on what kind of charge is on this outside surface. If it were a very large amount of charge, my graph might jump way up. All right, in this case, it's 2 microcoulombs. The conductor, the outer object rather, was overall neutral. And so what's really going to happen is we don't pick up quite where we started off. We pick up sort of like as though this line just kept on smoothly decreasing. But it was interrupted by the presence of the conductor between 10 and 11 centimeters. All right, so that would be my correct graph for this particular circumstance. All right, I will, in a separate video, treat the question of what if the middle thing had been an insulator, and also what if we've been talking about concentric cylinders instead.